Hello and welcome to another review session for your final exam in Calculus 3208, brought to you by CDLI. And in this session today we're going to be looking at how do we do or perform this mythical monster called implicit differentiation. Certainly one of the topics that students struggle with from time to time in this course, so hopefully this will be a real helpful one for you and we can figure out some of this crazy business that we call implicit differentiation. So let's take a look now at a couple of the things we're going to look at. We're going to talk about the idea behind implicit differentiation. So maybe if we can get an understanding of how this stuff works or what it really means, then actually performing these implicit derivatives or taking them will be easier to do. So differentiating implicit relations comes after that, the actual algebraic methods that we have to tackle. Okay? So the first thing we're going to do is we're going to look at an example and try and explain away what's really happening here. So we'll take the example of a circle. So x squared plus y squared equals 7. And if you saw the previous video to this one, you'll know that that's an implicit relation because we don't have y written as a function of only x when we write it that way. We could do that for this particular relation, but it would get a little bit messier than what we have to do here anyway. So what we want to do here is we want to remind ourselves with implicit relations, we've got our x and y variables kind of bouncing all over the place. It's not neat and tidy with y on one side and x is stuffed with x on the other side. So in order for us to make sure we get this done correctly, it's important to keep in mind that usually y is a function of x. So if we think about this here, we can say if y is a function of x, then what we can see is that x squared plus y squared equals 7 can be written as x squared plus f of x squared equals 7. And now what it's important for us to see is if I'm going to take the derivative, or I'm going to differentiate this entire expression here, basically what I have is one function nested inside another in a part of what I'm dealing with here. So if I look over here, I can see that I've got my f of x for this particular function, but it's hiding inside a power function, which is the stuff inside squared. So anytime I have to differentiate where I have a nested function, the only way I'm allowed to do that is if I use the chain rule. And that's really the kicker for implicit differentiation. Sometimes I tell my students when we differentiate implicitly, we have to use and abuse the chain rule. So take it to as far as we can with the chain rule. Okay. So let's start by finding a derivative of this. And we're actually going to use this function notation that we have here for the first step only, just to get ourselves used to the idea of why we're doing this. So if I want to differentiate my first term, which is x squared, not much to that, I get 2x. And everybody should be okay with that by now. Then I want to use what we call chain rule to differentiate the second stuff, which is this f of x here, inside brackets all squared. So chain rule would tell me I'd take 2 times f of x, reduce the exponent by 1, so you could put a 1 there, but we typically don't. So it's 2 times f of x multiplied by the derivative of f of x, and then on the other side I differentiate 7 and I get a 0. Now, so that's really, nuts and bolts wise, that's the difficult bit about implicit differentiation that sort of throws people for a bit of a loop. They don't realize, they just see x and y as 2 different variables. And then all of a sudden, they jump right into trying to do implicit differentiation, and there's y primes or dy over dx's and stuff all over the place, and it just gets really confusing. But really what we do with this now is instead of carrying f of x with all those brackets and all that funny function notation, we usually switch to one of two other forms. The one that I typically use is the Leibniz notation where we have a dy over dx. So I'm going to change my f of x into a y because we know that y equals f of x is kind of the same thing. And I'm not going to write f prime of x like that all the time. I'm going to write dy over dx instead. So basically what we have right here is the same thing that we have down here, just using a different notation. Okay, so if I start it with this expression right here, I'm going to be able to take that and get directly across all the way over to here without thinking about this stuff all the time, and that's kind of our goal. So what I'm going to do now is I'm just going to run through how I would differentiate this without thinking about the function notation, even though we just saw why it works. So let's say I have that x squared plus y squared equals 7, and I'm going to write the derivative for it, let's say down here. I've got some space. Okay. So I take x squared plus y squared equals 7. One more time. When I see the x squared, I know that's 2x plus the y squared. I've got to think of that as an f of x. So I've got an f of x inside a square. So that's a chain rule. So it's going to be 2 times my function, which we still call y, multiplied by its derivative, which you can call y prime, or as I prefer to write it, dy over dx. And the reason I prefer that is because sometimes my primes are hard to see or things happen and it gets confusing that way. So, and then on the other side, we've just got the derivative of 7 will be 0. So that's where this mysterious implicit dy over dx stuff gets stuck in the middle of everything. All right, so now what we're going to do, we tidy up our notation, and then the next thing we do is we isolate the derivative. So we want to get dy over dx all by itself. So I'm just subtracting the 2x here to get it over on that side. And then I'm going to divide both sides by 2y. And I have this. And then one last step to get rid of those 2's by division. And all I have is dy by dx equals negative of x over y. Okay? And that's how I take an implicit derivative for a simple example. Now, let's do some more complicated examples. And the one thing to keep in mind, remember, whenever we're doing implicit differentiation is always remember y is a function of x, so that's why we need to use the chain rule with it. Okay, so let's move along. Okay, so it says find dy by dx for, whoa, what a monster of a function this looks like. Okay, let's get started. So the first thing I want to do is just attack it by throwing derivatives at everything. So the first term is just a y to the power of 7, but remember that's an f of x inside a power function. So that's going to require a chain rule. So it's 7y to the power of 6 multiplied by the y which is inside, and the derivative of the y that's inside is dy by dx. Okay. Then I've got to subtract. And to differentiate this next really huge and disgusting term, I'm going to think of the negative 11 as being a constant multiple that I'll hold outside, and then I have to use a product rule on the rest of this stuff. Yipes. Okay. So the derivative first of x to the power of 5 will be 5x to the power of 4. Don't need to multiply by anything else there because x is just x. There's no function there other than just the x itself that's inside. So that's the derivative of my first term in this, or my first factor, sorry, in this pair. And I multiply that by y to the power of 6. So the derivative of the first times the second by product rule, plus the derivative of the second bit here will be 6y to the power of 5. But y is a function of x, so I need to tack on my dy by dx in there. And then multiply that by the first term, which was x to the power of 5. Okay. Then I subtract. The derivative of x to the power of 15 will be 15 x to the power of 14, and I don't need to multiply by anything there because x is not a function unto itself. It's just the one variable with which we are taking the derivative with respect to here, I should say. And that's going to be equal to, the derivative of 11 is 0, so I'll throw that out, and there's just a 0 on the other side. Next step in implicit differentiation. If you can get through that, that's the hardest part. All we do from here is just tidy it up. So how do we tidy this up? Well, what we're going to do is simplify everything here with the brackets and all that nonsense first. So I've got 7y to the power of 6 times dy over dx. And then I'll carry my 11 through using distribution. So I have negative 55 x to the power of 4, y to the power of 6, minus 66. And I'm going to write this in a different order. I'm going to say x to the power of 5, y to the power of 5, and then my dy over dx. Doesn't really matter, but that just looks a little cleaner, I think. And then we still have our minus 15 x to the power of 14 there. Okay, so after we get that far, then there's only really a two-step process. The first step is we collect every term that has a dy over dx in it on one side of the equation, and every term that does not on the opposite side of the equation. So I'm going to leave my 7y to the power of 6 by dy over dx, and my negative 66 x to the power of 5, y to the power of 5 by dy over dx, all on the left side here. And everything else has to move, so I'm going to add the 55 business to both sides. So I'm adding 55 x to the power of 4, y to the power of 6, and I'm adding 15, x to the power of 14 to the other side as well. So the reason we do that is because what you'll notice is that every term on the left, like we said, will now have a dy by dx in it. And since they all have dy by dx in them, then that's actually a common factor of every term over here. And this is what allows us to separate the derivative, dy over dx, from all the other garbage that we have floating around here. So I'm going to remove the dy over dx as a common factor now. And what's left in each of the terms when I divide it out will be 7y to the power of 6 minus 66x to the power of 5, y to the power of 5. And then that's equal to 55 x to the power of 4, y to the power of 6, plus 15 x to the power of 14. Okay. So one last step to do here. If I want to get dy by dx all by itself, I'm just going to divide both sides of my equation by all of this business that's in here. And when I divide that on both sides of the equation, of course, it'll cancel out on the left. And I'll just have my dy by dx over here. And on the other side, I'll have all the junk that we kicked out and moved to the other side of the equation, divided by all the stuff that was left when we factored the dy by dx out of the other terms, which is 7y to the power of 6 minus 66x to the power of 5, y to the power of 5. Okay? So there it is. That's an implicit derivative done in all of its gory detail. One thing I'm going to highlight right now before we go on to another example, this is the big thing. This product rule that we had to do up here, almost every time you're asked to find an implicit derivative, there's going to be product rule in it. So that's the one we got to be real careful about. So I think when I made up these examples, I tried to put a bunch of those in here. Alrighty, here we go. So we've got find dy by dx for x cubed y plus xy cubed. Okay, so let's tackle this. I've got a product rule here and another product rule there. So first product rule, derivative of the first thing is going to be 3x squared times the second thing, which is y, plus the derivative of the second thing. Y is a function f of x, so its derivative is f prime of x, or dy over dx multiplied by the first one, x cubed. So all of this is just the product rule to find the derivative of x cubed y. And then I'm going to add, using another product rule now, the derivative of the first bit in my second term will be just 1, because the derivative of x is 1, times y cubed, plus the derivative of the second bit will be 3y squared times dy over dx. Remember, because it's a nested function, y is a function of x, multiplied by the x that we had in the beginning. And then that's going to be equal to 0, because the derivative of 3 is 0. And everything I have inside here is just part of the product rule for these two terms. Okay? So two product rules. And now we don't have any brackets to get rid of, so I just collect what I want to keep on the left and kick everything else over to the right. So on the left, I'm going to keep, and I'm going to rearrange to make them look a little tidier, x cubed times dy over dx, and plus 3xy squared times dy over dx, and that's going to be equal to negative 3x squared y minus y cubed to get those terms to the other side. I factor out my dy over dx from each term on the left, 3xy squared, and that's going to be equal to the same thing again, x squared y minus y cubed. And then I divide both sides by that to get rid of it, and I just have dy over dx is equal to, and let's say we'll put the negative out in front and make those two terms positive, all over x cubed plus 3xy squared. Okay? So there's our implicit derivative, dy over dx, the old-fashioned way. Alrighty, let's try another one. So what's coming next now? We've got use implicit differentiation. So this is actually a question that I took directly from a test. So it says use implicit differentiation to find dy by dx for that particular function. They're all very similar, aren't they? So let's go at it. 3x squared, the derivative will be 6x, plus I'm going to leave the 2 as a constant multiple of a function, and that function happens to be a product. So xy squared, the derivative of x will be 1 times y squared, plus the derivative of y squared will be 2y, and it's a function, so it's got to have a dy over dx, multiplied by the x that we started with. So everything inside here is the product rule from that particular term. Then the y cubed will be 3y squared times the dy by dx. 19 becomes 0, and there's still 0 on the other side. So a little bit of distribution with the 2, and we have 2y squared plus 2xy dy by dx. And that's going to be plus 3y squared dy by dx again equals 0. Collect the dy by dx terms. So we've got 2xy times our friend the derivative plus 3y squared times our friend the derivative. And on the other side we'll have a negative 6x and a minus 2y squared. So factoring out here, we have dy by dx times 2xy plus 3y squared equals negative 6x minus 2y squared. And in the end, our last step here, we can say our derivative dy over dx will be equal to, I'm going to factor out the negative 1 there probably again. I like to keep it tidy there. So we've got 6x plus 2y squared with the negative 1 factored out, all over 2xy plus 3y squared. And le voila, there it is. We have our implicit derivative. Okay? So next is the your turn question. So yet another implicit derivative. Watch out for the product rule. Don't forget that y is equal to f of x. So you've got to use the chain rule with it all the time. Okay, good luck with that one, and I'll show you the solution now. So here's the solution to the your turn question in all of its gory detail. Alrighty, hopefully you got that right, and if not, you're figuring out how to get it right next time, which is the goal of all of this. And we'll highlight some of the key ideas from here. First thing, we say to differentiate an implicit relation, we use standard differentiation rules, but we treat all terms containing y as having a function y equals f of x. This implies that we have to use the chain rule and multiply by the derivative f prime, but the expressions written in terms of y, we multiply by y prime or dy over dx. Maybe your teacher uses y prime instead of dy over dx, but it's the same process. So after completing the differentiation, all terms containing the derivative we collect on one side. All terms that don't have the derivative go to the other side. Take out the dy over dx as a common factor. Divide both sides by the junk, and we have our derivative. I really hope that that was helpful, and I really hope your studying is going well and that you're going to really ace that calculus exam. All right. Good luck.